In this video, we're going to talk about the concept of electric potential energy. So let's begin our discussion with a picture. Let's say we have two parallel plates. The first one, the one on top, is going to be positively charged. The second one is going to have a negative charge. Now we know that the electric field will extend from the positively charged plate and it's going to point towards the negatively charged plate. Now let's say we have a positive charge between these two plates. This positive charge will feel a force that will accelerate it in the same direction as the electric field, which in this case it's going to be the negative y direction. A negative charge will feel a force that will accelerate it in the opposite direction of the electric field. Now let's say this is point A and the charge is moving to point B. How can we determine the electric potential energy at each of these points? So let's say that point B is at a position YB above the negatively charged plate, and point A is at a position YA above the negatively charged plate. So here's what we can do to come up with a formula to calculate the electric potential energy. So we're going to start with this. The work done going from A to B is going to be equal to the negative change in potential energy. So potential energy, you could represent it as PE or capital U. You need to be able to distinguish gravitational potential energy from electric potential energy. Some textbooks will use U sub G to represent gravitational potential energy, which is mgh. Others will use UE to represent electric potential energy. And some will just use PE, so be careful with those differences. Let's use capital U in this video to represent electric potential energy. Now we know that the work is equal to the force times the displacement. And going from A to B, we have the change in potential energy. So final minus initial. The final potential energy will be at B, and the initial electric potential energy will be at A. Now the electric force is equal to the magnitude of the electric field times the charge. So we can replace F with E times Q. Now D represents the displacement. So as we move from A to B, the displacement is going to be the change in position. So it's YB minus YA. By the way, let's take this negative sign and let's move it to the other side. So I'm going to make this positive, make this negative. So the displacement is Y final minus Y initial, or YB minus YA. Now let's distribute negative EQ. So we're going to have negative EQ times YB, and here we have two negative signs, so it's going to be plus E times Q times YA. So UB is equal to negative EQ YB. Negative UA is equal to positive EQYA. If you multiply both of those by negative 1, you'll get that positive UA is equal to negative EQYA. So we can thus say that the potential energy, the electric potential energy, is going to be negative times the electric field times Q times Y. So this is the equation that can help you to calculate the electric potential energy. Notice how it's similar to the gravitational potential energy, which is equal to mgh. In both cases, the potential energy is dependent on the position from ground level. In this case, the negatively charged plate can be considered the ground level of this particular structure. Let's work on this problem. A 50 microcoulomb point charge moves from point A to point B as shown in the diagram below. The magnitude of the electric field is 2 times 10 to the 6 newtons per coulomb. Points A and B are 80 centimeters and 20 centimeters above the negatively charged plate respectively. Part A. Calculate the electric potential energy at points A and B. So we know that this positive charge is feeling an electric force that's going to accelerate it towards the negatively charged plate. And we know that B is 20 centimeters above the negatively charged plate, and A is 80 centimeters above it. So to calculate the electric potential energy at these points, we could use this formula. The electric potential energy is going to be negative times the electric field times the charge times the position above the negatively charged plate. So what's E? We have the magnitude of E is 2 times 10 to the 6. But notice the direction of E. E is going in the negative y direction. So for this formula to work, we need to plug in negative 2 times 10 to the 6 newtons per coulomb. And then we have the charge. So Q is positive 50 times 10 to the negative 6. And then we need to plug in the height. So let's calculate the potential at A first. So if we calculate the potential at A, we need to use the position at A. It's 80 centimeters, so that's going to be 0.80 meters. So the two negative signs will cancel, which will give us a positive answer. So the electric potential energy at point A is going to be 80 joules. Now let's calculate it at point B. So it's going to be negative times negative 2 times 10 to the 6, and then 50 times 10 to the negative 6, but this time times 0.20. So UA is going to be 20 joules. So that's how we can calculate the electric potential energy. This is supposed to be UB, my mistake. So that's how we can get the electric potential energy at those 2 points. Now what can we say about the change in electric potential energy as well as kinetic energy going from A to B? Is it positive or negative? And what about the work done on a positive charge going from A to B? Is that positive or negative? Well, the electric potential energy is decreasing as we move from A to B. We went from a value of 80 to 20. So the electric potential energy is decreasing, which means that the change in electric potential energy is negative. As the electric potential energy decreases, the kinetic energy will increase. As the electric force accelerates the positive charge towards the negatively charged plate, the speed of the charged particle is going to increase, so the kinetic energy is going to increase. And since work is equal to the change in the kinetic energy, if the change in kinetic energy is positive, the work done on the charged particle will be positive. Another way in which you can determine the sign of work is looking at the force and the displacement vectors. If these two vectors are in the same direction, the work done is positive. If they're opposite to each other, the work done is negative. If they're at right angles to each other, the work done is 0. The charged particle is moving in the negative y direction, so its displacement vector is downward. Since these two vectors are in the same direction, the work done is going to be positive. But now let's go ahead and calculate the work done in this example. So work is equal to the negative change in potential energy. So that's going to be the final potential energy minus the initial potential energy. The final, or UB, is 20. The initial is 80. So it's going to be negative 20 minus 80 is negative 60. So as we can see, the work done is positive 60 joules. So that's the answer for part B. So that's how we can calculate how much work is done going from point A to point B. Now let's move on to part C. What is the electric potential at points A and B? Before we answer that question, let's erase a few things and rewrite some of our values above. So with this information and everything else that we know, how can we determine the electric potential at points A and B? The electric potential is equal to the electric potential energy divided by charge. So make sure you understand that. The electric potential energy, I'm going to write EPE, that's capital U. V represents the electric potential. The electric potential energy is measured in units of joules. Electric potential is measured in volts. 1 volt is 1 joule of electric potential energy per 1 coulomb of charge. So electric potential measured in volts is the ratio of electric potential energy in joules per unit charge in coulombs. So if we wish to calculate the electric potential at point A, it's going to be the electric potential energy, which is 80 joules, divided by the charge. And the magnitude of the charge is 50 microcoulombs, or 50 times 10 to negative 6 coulombs. So this is a very large number. It's 1.6 million. So we can say 1.6 times 10 to the 6 volts, or just keep in mind 10 to the 6 is mega, so we could say 1.6 megavolts. You could also say 1600 kilovolts. Maybe that will be a better value to deal with here. Now let's calculate the electric potential at B. It's going to be 20 joules divided by the same charge. So that's 400,000 volts, which is 400 kilovolts. So that's how we can calculate the electric potential at each of these points if we know the charge and the electric potential energy. Now we can also confirm this answer. Another way in which we can calculate work is by using this formula. The work required to move a charged particle through a potential difference is equal to negative Q delta V. So Q is positive, it's 50 times 10 to the minus 6. And we're going from A to B. So going from A to B, the change in voltage as we go from 1600 kilovolts to 400 kilovolts, the change in voltage is negative 1200 kilovolts. It's final minus initial. 400 minus 1600 is negative 1200. So this is negative 1200 kilovolts, or negative 1200 times 10 to the 3 volts. And this will give you the same answer, positive 60 joules. So in all cases, we can see that the work done on this charge to move it from point A to point B is going to be positive. Now I'd like to take a minute to highlight the similarities between gravitational potential energy and electric potential energy. So let me just clear away a few things. So electric potential energy is dependent on the height. In this case, we'll call it y. Now, when we analyze an object that could fall under the influence of gravity, the gravitational potential energy is also dependent on the height. The gravitational potential energy is equal to the mass times the gravitational acceleration times the height. The electric potential energy is equal to the charge times the electric field times the height. So note the similarities between these two equations. These are both forms of potential energy. So here we have charge, here we have mass. Here we have the electric field, and here we have the gravitational field, or the gravitational acceleration. And then both of them are dependent on the height. So if you can remember this equation, that will help you to remember this one as well. Number 2, a 70 microcoulomb charge is located at a point where the electric potential is 300 volts. What is the electric potential energy of this charged particle? We know that electric potential is equal to the electric potential energy divided by charge. But in part A, we want to calculate the electric potential energy. So rearranging that equation, or multiplying both sides by Q, we get that the electric potential energy is equal to the charge times the electric potential. So we have a 70 microcoulomb charge, and the electric potential is 300 volts. Keep in mind, 1 volt is equal to 1 joule per coulomb. So instead of writing 300 volts, we can write 300 joules per coulomb. So we can see that the unit coulombs will cancel, giving us the unit joules. So it's 70 times 10 to the negative 6 times 300. So the answer for part A, the electric potential energy will be 0.021 joules. Now let's use the same formula for part B. So it's going to be U is equal to QV, and this time we have a negative 60 microcoulomb charge. So since electric potential energy can be positive or negative, we're going to plug in negative 60 times 10 to the minus 6. And this time, the electric potential is 500 instead of 300. And so this is going to be negative 0.03 joules. So that is the electric potential energy of a negatively charged particle with an electric potential that's positive. If we had a negatively charged particle with a negative electric potential, the electric potential energy will be positive because the two negative signs will cancel. So for instance, let's say we have a negative 90 microcoulomb charge located at this point where the potential is negative 400. So using this formula, we're going to get a positive result. It's going to be negative 90 times 10 to the minus 6 times negative 400. And that's going to be positive 0.036 joules. So the electric potential energy could be positive or negative. Number 3, a 100 volt battery is connected to 2 oppositely charged parallel plates that are separated by a distance of 10 millimeters. Calculate the electric field. So here we have the direction of the electric field. We have the voltage of the battery, it's 100 volts, and we know the distance between the 2 plates. The formula that we need to calculate the electric field is this formula. It's equal to the change in voltage divided by the displacement. For those of you who want to keep it simple, you could say it's the voltage across the plates divided by the distance of the plates. But for those of you who want to be more technical, there is a negative sign involved. But let's keep it simple. We're just going to use V over D. The voltage is 100. The distance between the plates is 10 millimeters, which is, to convert that to meters, you need to divide by 1,000. There's 1,000 millimeters in 1 meter. So 10 divided by 1,000, this gives us 0.01 meters. So the electric field is 10,000 volts per meter. The electric field tells us how the electric potential changes over distance. So for every 1 meter that you move, the electric potential changes by 10,000 volts. Now if we want to get it in volts per millimeter, we could have done this. We could have done 100 volts divided by 10 millimeters. And we could say that the electric field is 100 divided by 10 is 10. So it's 10 volts per millimeter. So if we move by a distance of 1 millimeter in this between these parallel plates, the electric potential will change by 10 volts. So let's say at this plate is 100 volts, at this plate is 0 volts. Let me put these numbers over here. So let's put 0 over here and 100 over here. And let's say this is the distance between the plates. So here it's at 0 and here it's at 10 millimeters. If we were to move 1 millimeter above the negatively charged plate, the electric field will change by 10 volts. If we move another millimeter, it's going to increase by 10, so now it's going to be 20. In part B, we want to calculate the electric potential at a point 7 millimeters above the negatively charged plate. So 7 will be maybe somewhere over here. So this is going to be an electric potential of 70 volts. To get that answer, you could simply rearrange this formula. The electric potential, V, is going to be the electric field times the distance. So the electric field, using this one because we have the unit millimeters, it's going to be 10 volts per millimeter. And then if we move a distance of 7 millimeters, these units will cancel. It will be 10 times 7, and that will give us an electric potential of 70 volts. So that's how you can calculate the electric potential at any point between the two parallel plates. It's simply the electric field times the distance. But you do need to pay attention to the units. You want to make sure that the units match if you're going to use that formula. Now let's talk about the formula above. For those of you who want to understand the negative sign and how it works, let's get rid of a few things. And we'll talk about how we can derive that formula. So let's say if we have a positive charge and it's moving from position A, where the potential is 70, to position B, where the potential is 20. So as we move from A to B, how is the potential changing? The final potential is 20. The initial potential is 70, so the change is negative 50. Now the displacement relative to the negatively charged plate is, what's D? The displacement is going to be negative 5 millimeters if we move from point A to point B, because we're going down the negative y-axis. If you take displacement as the final position minus the initial position, this is your final position 2 minus your initial position 7, so you get negative 5. So here we have negative 5 millimeters. So it's negative, and then 20 minus 50 is negative. So we have a change in potential of negative 50 and divided by negative 5. So these two will cancel. So we have positive 50 volts divided by negative 5. And so we're going to get negative 10 volts per millimeter. So what we have here, this is just the magnitude of the electric field. But in fact, it should be negative. The reason why it's negative is because the electric field is moving in the negative y direction. So that's the purpose of the sign. It tells you the direction of the electric field. But since we already know the direction, we really don't need to worry about the negative sign. We could say the electric field is simply the voltage across the plates divided by the distance between the plates. You could just use this to determine the direction, but if you know the signs of the plates, you can easily determine the direction of the electric field. It's always going to move from the positive plate toward the negative plate. But now you understand how to use this negative sign in that formula. Now let's talk about how to derive that formula. You can start with this equation. Work is equal to, this is the work done by an electric force, is equal to negative Q times the potential difference through which that charge is accelerated. Now work is equal to force times displacement. And the electric force acting on a charged particle in an electric field is equal to the electric field times the charge. F is equal to EQ. So to calculate the electric field, we need to divide both sides by QD. QD will cancel on the left, but only Q will cancel on the right. And so we're left with this equation. The electric field is equal to negative times the voltage divided by the displacement. So that's how you can derive that formula. Now let's move on to part C. What is the electric potential energy of a 400 microcoulomb charge placed 7 millimeters above the negatively charged plate? So we want to calculate the electric potential energy at point A. So we have a charge at point A, but we also have the magnitude of that charge. To calculate the electric potential energy is simply the charge times the electric potential. So we have a 400 microcoulomb charge, and at 7 millimeters above the negatively charged plate, the electric potential is 70 volts. Let's convert microcoulombs to coulombs. So this should be 400 times 10 to negative 6 coulombs. And then we'll multiply that by 70 volts. So the electric potential energy is going to be positive 0.028 joules. So that's how we can use that formula to calculate the electric potential energy. Now let's confirm our answer with the other formula that we've used for this situation. So if you recall, the electric potential energy is also equal to negative times the charge times the electric field times the height above the negative plate for a positive charge that falls towards the negative plate. And let's put it over here. So Q is positive 400 times 10 to negative 6. The electric field, and I just got rid of it, but it was 100 volts divided by 0.01 meters, so it was 10,000 volts per meter. Now the electric field is going in the negative y direction, so we need to apply that negative sign to get this right. And the height above the negatively charged plate, point A is 7 millimeters above it. Now this is in meters, so we want this to be in meters as well. 7 millimeters, if you divide that by 1,000, that's going to be 0.007 meters. If we use the electric field in volts per millimeter, then we could use millimeters here. But you want to make sure that these units, they match. So it's negative 400 times 10 to negative 6 times negative 10,000 times 0.007. And this gives you the same answer, positive 0.028 joules. So both formulas work. So now you have two ways in which you can calculate the electric potential energy above some reference point. It's equal to the charge times the electric potential, and it's also equal to the charge times the electric field times the height with a negative sign.